Hello, my name is Carl Kronberg, and I will be talking to you today about a collection of tools that we've built to help with the debugging of memory. And so the motivation for this work is that program errors caused by unknown bugs ultimately lead to misdirected programmer effort. So, for example, in a memory corruption bug in the hotspot Java virtual machine, a comment on this slide describes how the programmers had difficulty narrowing down the source of an error. And so in this talk, I will present Permchecker, a series of debugging tools aimed at reducing that sort of confusion in the presence of these rogue memory corruption errors. And so what did we do? Well, first off, we built a DSL compiler, which reads in a specification of a heap layout. And from that, it generates a collection of artifacts for manually annotating a memory manager or sufficiently low-level application that works directly with raw addresses. Second off, what we did was built an LLVM extension, which ultimately drives the instrumentation of certain compilation units with permission tracking instructions. And so finally, what we did is at runtime, we built a dynamic analysis tool in the PIN framework. And that tool, what it does is manages memory access permissions in a shadow memory map and detects corruption as memory access violations. So what is memory corruption, though? Memory corruption is often an operation which simply accesses memory of the wrong type. In a memory manager, though, defining what it means for a memory corruption to have happened is not quite that simple. So dynamic address manipulations are designed to compute pointers interior to some structure. And for example, a function reporting whether or not an address references memory in the heap must recognize the type of an object located at the beginning of a heap block, that's distinct from the same address referencing raw heap memory comprising the block being bigger than the object it's containing the object. And so as a result, memory types within existing memory manager implementations must ultimately be manually managed in order to recognize violations of these sorts of more nuanced distinctions. So what we do to model these distinctions with Permchecker, that is to define type states of memory. Now, a type state includes three pieces. First, a type defines the shape of heap memory. Second, state transitions define which addresses take on those types at different points during execution of the program. And third, access permission annotations model the permissible behaviors, what memory can be accessed and when. Note that the usual application of type state that some will be familiar with in a static setting requires the definition of an appropriate meet function over the semi-lattice of allowable type states. In contrast, this dynamic application doesn't require approximating the type state of memory, and that's because it's known by observing a dynamic execution trace. So the first piece of Permchecker is a DSL, the syntax of which is defined on this slide. In it, a type state of memory is a statically known unique identifier. These identifiers have structural relationships, including sequencing of memory, as well as a union structure, which is just a way to define multiple ways to view the same piece of memory. The most common view being memory is either allocated or it's free. Now, these pieces of memory are built up from just the raw primitives that we're all familiar with, like bytes and words, each implying a memory size, but not the contents, not the type of the value located in it. These sizes can then be scaled by a constant integral multiplier, as seen on the second to last line of these BNF rules. So, for example, a region of memory here defined on this slide is a superstructure containing a sequence of some number of allocated objects, followed by some number of free, unallocated words of memory. Note here that the pound symbol is a prefix variant of the Kleene star regular expression operator. So these objects then have their own substructure as defined on the third line here. Taken all together, these type state declarations in this particular example define the layout of the heap managed by the hotspot Java virtual machine. Now, given that heap layout for the JVM, the DSL compiler generates a library of boilerplate code, which helps us reduce the annotation burden for the programmer specifying where each type state transition occurs. Now on this slide, we see a set of generated type states for use, in this case, in C++ code. The insight here was to assign each type of memory, such as a mark word or a class pointer, to assign each of them a unique identifier based on the context in which it can be allocated. So for example, type state number 5 here represents a mark word on the Java heap in hotspot, whereas type state number 30, in contrast, can represent a mark word allocated onto the C++ stack. So those generated type states can then be applied as permissions. Function and class annotations, as enabled by an LLVM extension here, allows us to define the validity of memory accesses as they relate to compilation units in the source code, in the implementation of the memory manager, such as, in this case, the LLVM annotation shown on this slide, which states that this compare and swap function is allowed to both read and write any kind of mark word or any kind of object pointer. Note here that on line 116 of this function, we've actually included a similarly purposed manual type state check. Notably, this check expect operation, it's a kind of dynamic type checking assertion. It requires an explicit address as well as a size to check against, to check the type state for this piece of memory. Whereas the LLVM annotation we built achieves the same purpose, but only requires the type states of interest that this function is allowed to access. And so just stepping out a bit, care was ultimately taken to make these annotations not require a lot of architectural modifications to the system of interest. Instead, what happens is the LLVM extension handles the compiling of type state annotations into dynamic callbacks into a pin tool. So pin is a dynamic binary instrumentation framework. The tool we built in it receives type state information, both transitions and active permissions of the code currently running. Now, based on that, what it does is detect and report type state access violations. So an access violation is shown here on this slide, where the Java virtual machine expected to access a forwarding pointer, but was in fact observed to have accessed a mark word in an object's header. So the idea in reporting this kind of violation is to mimic existing ad hoc runtime assertions as found in the memory manager, in a memory manager. But by doing so, providing more effective diagnostic value out from such a report. So for instance, on lines here 6 through 11, what we get out from a violation report is a kind of enhanced core file, which that includes some of the context, what was around the violated address, as well as all of the context. So we also dump out a type state map at the point of failure. So to validate that diagnostic value of using this tool, our experimental analysis, we looked at both breadth and scale. For breadth, we report in the paper our subjective experience annotating type states in 3 systems: in a manual memory manager, DL malloc, as well as automatic memory managers of Jegs RVM, and ultimately, chronologically last, hotspot. Now, on the right of this slide is a breakdown of the modifications we had to make to hotspot. The key takeaway here is that there were 144 places, lines in the code, in which Java heap memory could change type state. And for those type states, there were 64 places in which we needed to add function annotations related to those type states. Lastly, what we have here is the remaining around 1,600 lines of code, which is accounted for in the lines added row. Those actually correspond to some custom glue code we had to write for managing type states directly as it relates to, or as was necessary in C++, Java, and ultimately generated assembly code, getting those to be able to communicate together. Now, for scale, that was breadth. For scale, what we did was we defined and reported on some objective measures of corruption detection capabilities of this tool, of Permchecker. So what we have here on this slide, what we can see is Permchecker's ability to detect a series of synthetic bug injections as compared to what we have available to us, which are existing runtime assertions found in the hotspot JVM. So for example, the second row in this table corresponds to 836 unique injections of use after free bugs, which happen to read freed memory erroneously. And so what happens here is nearly all of them are able to be detected by Permchecker, as shown in the next column, except for 4 benign ones, 4 ones that happen to not actually corrupt memory. In contrast, about half of them, only about half of them, show up as operating system errors or incorrect program behavior from the system when it doesn't crash but produces the wrong result in the application. And that's in the absence of Permchecker. Without Permchecker enabled, this is what you would see in hotspot with the same synthetic bug present. So based on this analysis at scale, we believe Permchecker to be an effective debugging mode to be considered for use in low-level systems development. Ultimately at the cost, in this case, in the case of hotspot, of around 2 to 3 months of developer time annotating and validating the most crucial aspects, pieces of the memory manager, of being able to allocate application level Java objects. So in considering Permchecker, some of its downsides include the following. First off, it has relatively slow debugging times, and those are comparable to that of Memcheck, ultimately because of its similar checking model of using shadow memory to track type states for each and every read or write operation in the program. Second off, what we have is a programmer effort must also essentially go into maintaining some of these, that glue code I mentioned, custom foreign function interfaces when type states are able to be changed in non-native code, which is often the case in a memory manager or in a virtual machine where we have generated assembly code. Last off, while the pin tool that we built is itself thread safe, you can run this with multi-threaded applications. It does not actually in any way guarantee the reproducibility of a memory corruption, where a memory corruption might be contingent on thread scheduling, and Permchecker can affect that in unfortunate ways sometimes. So thank you so much for listening today and hearing about my work. and I hope you enjoy the rest of OOPSLA